Hi, my name is Alexander Spiegelman, and I'm going to present in search for an optimal authenticated Byzantine agreement. Byzantine agreement is a long-standing problem in distributed computing in which parties communicated via message passing to agree on a single value despite some of the parties being malicious. For many years, Byzantine agreement considered to be a theoretical problem, but with the recent blockchain use case, it is becoming more and more practical. In particular, scalability is becoming one of the main concerns. There are three main network models to reason about Byzantine agreement. The stronger one is synchrony, in which all parties have the same clocks and messages arrived within a known bound. This model was mostly used in theory since we cannot rely on synchrony for safety in real networks. On the other extreme, there is asynchrony, in which messages can be delayed for an unbounded amount of time before delivered. The famous FLP results showed that deterministic solutions are impossible, and for many years randomized asynchronous Byzantine agreement considered to be impractical due to their complexity and inefficiency. Therefore, to deal with asynchronous periods in real-world networks, the practicals community adopted the eventual synchronous communication models. An eventually synchronous execution starts with an asynchronous period, but there is a global stabilization time called GST, after which the communication is synchronous. Therefore, naturally, to increase scalability, state-of-the-art practical Byzantine agreement protocol focused on reducing communication complexity after GST. Indeed, in recent years, there were many works in the eventually synchronous model that try to achieve linear communication complexity after GST. These protocols operate in a view-by-view manner. Each view has a designated leader that tries to drive progress. If one of the leaders is bad or the network experiences asynchrony, parties perform the view change to start over with new leaders. The Ziva and SBFT presented a linear fast-path communication in each of these views. Later, Hotstaff achieved a linear view change mechanism, but required that all honest parties start each view roughly at the same time. To this end, they assumed the pacemaker abstraction. and a few later works gave an efficient implementation of this pacemaker. For example, Noor et al. Showed an implementation that is communication efficient and expectation, and Bravo et al. Showed a memory efficient implementation. However, none of these works could provide a linear solution in the worst case. Therefore, we should ask ourselves, can we even hope for linear communication solutions? And unfortunately, the answer is no. First, a famous law bound by Dolev and Wychuk proves N-square communication complexity even for synchronous networks. In addition, previous protocols focused on communications after GST, but we should also ask what can be guaranteed before. In fact, we proved that no deterministic protocol can bound communication before GST. Moreover, there is no such thing as GST in practice. It is not like we can pay the price before GST once at the beginning of every execution and then enjoy synchrony forever. An execution in real networks consists of alternating periods of synchrony and asynchrony. So to conclude our observation, the eventual synchrony assumption was very useful in abstracting away the asynchronous periods of real networks to circumvent the FLP impossibility. However, it fails to capture the performance aspect required by modern use cases. On the other hand, asynchronous solution used to be too complex and costly for practical needs, but recently, with the help of modern crypto, they are becoming more and more practical. And in fact, state-of-the-art protocols match the N-square law bound by Dolev and Wychuk. These observations lead us to our approach. We forego eventual synchrony and instead hope for synchrony but prepare for asynchrony. In other words, we optimistically run on efficient synchronous protocols during the synchronous periods and fall back to randomized synchronous protocols whenever we feel that we are in asynchrony. Given the fact that communication before GST cannot be bound, we believe that it makes much more sense to run an efficient quadratic randomized protocol during asynchronous period than keep wasting bandwidth while waiting for asynchrony to run a linear protocol. Now let's talk about the result in these papers. We consider a single-shot Byzantine agreement, a computationally bound adversary, n equal 3t plus 1 players, where t is the threshold that the protocol, the threshold of failures that the protocol can tolerate, and f is the actual number of failures. We distinguish between synchronous and asynchronous ones, and our goal is to design a protocol with optimal communication cost under all network conditional failure scenarios. We generalized Dolev and Dwychuk to prove that any synchronous deterministic Byzantine agreement has theta ft plus t communication complexity. Note that when the worst case, when f is equal t, we get t squared lower bound, which coincide with the Dolev and Dwychuk lower bound. We then match the lower bound by showing that there is a deterministic synchronous authenticated Byzantine agreement protocol with order ft plus t communication complexity. And finally, we show that there is an authenticated Byzantine agreement protocol with order ft plus t cost in synchronous ones and expected order t squared cost in all other ones. To achieve our asymptotically optimal optimistic Byzantine agreement, we carefully combine our optimal adaptive to failure synchronous protocol with a variant of the VABA protocol for fallback. I will next present the high-level details of the protocol. The main building block is a linear communication leader-based view, LBV for short, abstraction, that gets a sequence number and a designated leader. It encapsulates it in a single linear implementation of a view, where similar to Hotstaff or VABA, there are three all-to-all and there are three all-to-leader. There are three leader-to-all and all-to-leader phases of communication. In each phase, the leader aggregates all messages to a single threshold signature and sends to all. For example, similarly to Hotstaff, a sequential composition of LBVs with linear view change mechanism in between is safe. One way to get synchronous Byzantine agreement protocol is to run t plus 1 sequential LBVs, each with a different leader. Note that since we are assuming synchrony, we don't need to deal with the costly pacemakers. Instead, we predefine the times when each view starts and ends. In addition, one property of an LBV abstraction is that when the leader is honest, all honest commit in this LBV. And since at least one leader is honest out of the TF plus 1 leaders, designated leaders, all honest commit by the end of the protocol. This indeed gives us a synchronous Byzantine agreement. However, the communication complexity of this protocol is t squared. And remember that our goal is to achieve an adaptive to the number of failures communication. Therefore, to improve the communication complexity, before starting an LBV, each leader checks if it is already committed, if it already previously committed a value. In which case, he keeps quiet and its LBV has no communication cost. If the leader keeps quiet, he sends no messages, then he gets no replies, and nobody sending messages in this LBV. So since each party gets a chance to be a leader, all honest will decide by the end of the protocol. Since all honest decide in the first LBV with an honest leader, we get at most one not quite honest leader. F Byzantine parties can cause at most order FT communication cost, since the communication of every LBV is order FT. So if F Byzantine leaders decide to drive their LBVs, we in total get order FT. Therefore, we get a total communication complexity of order FT plus T, one LBV with good leader, and at most F with bad. For the asynchronous fallback, we use LBVs to implement a variant of VABA to get liveness in expected constant number of rounds with older T-square communication complexity. Very briefly, we run n LBVs in parallel, wait for enough to finish, and then elect one LBV at random. You can find more details in the paper, but I don't want to spend time on this since it is not our main contribution. Now let's combine the pieces. When we run the fallback after our synchronous protocol, safety follows from the sequential composition in LBVs. In addition, liveness follows from the protocol guarantees. In synchronous runs, we know that all honest parties decide in the synchronous algorithm, and as we will show, in all other runs, in asynchronous runs, all parties fall back to the fallback protocol, and liveness is guaranteed by the VABA properties. So the question is how parties know when to fallback. Remember that we want to achieve older FT plus T cost in synchronous runs. Therefore, parties should fall back only in asynchronous ones, and also the mechanism to decide whether to fall back or not cannot cost more than older FT plus T in synchronous ones. So to this end, we add a glue component which we call help and try halting. After the synchronous part, each party that have not yet decided that have not decided in the synchronous protocol sends an help request message to all other parties. Of course, parties cannot tell if the run is synchronous or not, but if at least one honest knows the commit, it will answer to all help requests, and all honest will commit. So as long as the party gets less than T plus 1 help requests, it does not fall back. Know that less than T plus 1 help request means that at least one honest got a commit, and they will be able to help all others. However, once a party gets at least T plus 1 help request, it aggregates it via threshold signature and forwards to all. Once a party gets an aggregated message, it forwards it and continues to fallback. Know that due to the forwarding, if one honest fallback, that all honest fallback and termination guaranteed by the fallback properties. Okay, so to analyze the protocol, by the property of the synchronous protocol, all honest decide, and thus at most T parties send an help request. Only the Byzantine might send help request. Therefore, no honest party will fall back, because in order to fall back, an honest party needs to see T plus 1 help request. The cost of try helping, therefore, is order FT plus T in synchronous runs. Remember that since all honest parties decide and commit in the synchronous part, none of them send help requests, and thus they cause nothing in the communication cost. And each Byzantine party can cause at most T messages, because it will send an help request and received at most n help reply. Thus, the overall cost in synchronous runs of our protocol in synchronous runs is order FT plus T. We get order FT plus T from the synchronous protocol, and another order FT from the halting mechanism, for the help and try halting mechanism. The cost in all other runs is order T square, in expectation due to the fallback guarantee. To summarize the contribution in the paper, we proved that eventually synchronous deterministic Byzantine protocols require unbounded communication complexity before GST. We then proved the lower bound of theta FT plus T for even synchronous Byzantine Agreement protocols. Then we presented a matching upper bound with communication cost older FT plus T, which we believe is interesting by itself due to its optimal adaptive to failures communication complexity. And finally, we gave an optimistic protocol that achieves older FT plus T complexity in synchronous runs and older T-square complexity in all other runs. I also want to briefly mention a future work in which we adapt our hope for synchrony but prepare for asynchrony to the practical world. This is a joint work with Rati, Lefteris, Alberto, and Julon, in which we combine a two-chain variant of hot stuff with an asynchronous fallback to achieve a practical solution that enjoys both robustness and an efficient fast path. Compared to this paper, we trade the optimal older FT plus T adapted to failures communication complexity for better latency in the best case. Lastly, on the theoretical side, this paper leaves a few open questions. First, early stopping. Is there a synchronous protocol with older FT plus T communication cost that stops after older F rounds? Note that our protocol in this paper requires exactly n LBVs, which is older n rounds. The second open question is optimal resilience. In our protocol, we assume that the number of parties n is equal to 3t plus 1, since it is the best we can do in asynchronous runs. But we wonder if there is a synchronous protocol with older FT plus T communication cost that tolerates a minority of Byzantine failures. Third, the third question is whether we can sync-convert our lower bound with randomization. In other words, is there a randomized synchronous protocol with less than FT plus T communication cost? Okay, thank you very much for watching the video, and I hope to see you soon in the future in some in-person conference.